Hey gang, welcome back to Math 3440. Today we're going to discuss assessing normality and how we use graphics to do that. So we've discussed a few types of graphs we'll use to assess normality or how the average statistician uses them, but today we're going to go over a few that I think are important because it's important to determine whether a data set is normal, because that allows us to do certain things to it using certain types of procedures that require our data to be normal versus and also if the data is not normal, it tells us, okay, well then you have to rely on these other kinds of methods to assess your data overall, or find come to some realizations or findings about your data. All right, and so assessing normality is a big important part of the pre-process after you've collected your data to before you can do other processes. And we do that graphically. So as I said, many statistical procedures need us, after we require that we draw a sample from a population whose distribution is roughly normal. Okay. Often we don't know whether the population is approximately normal when we draw a sample. Okay. I mean, very rarely do we. So the way to assess whether the population is truly normal or not is to examine the sample and specifically graphically examine the sample. So there are three important ideas to remember here when we assess normality. Number one, we're not trying to determine whether the population is exactly normal. What does that mean? That means there's no such thing as a perfectly normal data set that you'll collect randomly from a population. It's just not possible to be exactly normal, but you can be approximately normal, which is something we'd like. Okay. Number two, assessing normality is more important for small samples than for large samples. Now, a caveat to that is that yes, it's always important for small samples, because when you take a small sample size, if that thing's skewed, you're going to be giving your results that come out of it will be also misleading. So they need to be as normal as possible if you're going to use a normal method to look into the data further. But for large samples, it's still somewhat important. We still should do it, but it's definitely more important for small than large. Okay. Number three, hard and fast rules when we're assessing normality do not work well. Now today we're going to discuss a few hard and fast rules, and two of the three of them I totally agree with. One of them, just for our purposes in the course, we're going to stick to these three things, but note that when I mention those three, the first one is going to be taken with a grain of salt, because there's conflicting beliefs out there in the stats world. Okay. So how do we know when do we reject the idea that or reject the assumption that our data set's normal? Well, if a data set, when we graph it or we look into it a little further, has any of the three following criteria, then we're going to say that the data is not normal, and we probably need to look at other procedures to analyze our data further. So the first one is the one I'm talking about, being one that I don't 100% agree with, because this one here has conflicting viewpoints depending on who you ask. But a lot of textbooks say if a sample contains an outlier, the data is not normal. So this is stipulation number one. The second criteria here says that if the sample exhibits a large degree of skewness, then we'll consider the data not normal. That one's a tried and true one. That one always works. If your data's skewed heavily, the data is definitely not normal. Okay. And the emphasis here should be on the word large. Like when we talked about box plots, for example, we talked about one whisker being predominantly larger than the other, and that would give us an idea that the data set was skewed. Well, that's true, but it needs to really, when that word large needs to be taken into account. It has to be a large degree of skewness before we say the data is not approximately normal. Okay, we'll look at an example of that here shortly. The third criteria says that if a sample has more than one distinct mode, aka it's bimodal or has multiple modes in it, say something like this, or more than one hump, then the data is definitely not normal. And that one's true. That one's a hard and fast rule we can abide by. The first one, the reason I say that, if a sample contains an outlier, it usually skews the data, especially if it's above an outlier, just a single outlier above or below a data set. It's definitely going to skew the data set. But if it's not an outlier that's insanely out of bounds, and you can get some that are pretty close to, just falling outside that lower or upper outlier boundary in a box plot, for example. If it's just barely outside, sometimes we can do other tests on the data to determine whether the data set's normal or not, and some of those will come back saying it's normal. So outliers, it's kind of a contentious thing out there. Most textbooks say if it contains an outlier, say the data is not normal, and then some other people go, well, you can have one or two outliers and still get a fairly normal data set. All right. So I just want you to keep that in mind. But if we see an outlier for our class, we're going to say the data set's not normal. Okay. But if the sample has none of the preceding features, we'll treat the population as being approximately normal. So the rest of the lecture is really going to be examples of mostly of plots we've seen. We'll go over a new type today that's very important in assessing normality, but all of the plots we've talked about so far, there's several of them that work for assessing normality. The dot plot is one of them, especially if you have a small data set. So in example 1, they were doing a test on the accuracy of an oven thermostat. All right, the oven is set to 360 degrees, and the temperature when the thermostat turns off is recorded. So they're trying to test to see if this thermostat is cutting off the oven when it should. So a sample of size 7 yields the following results. And then below we see the dot plot. So the question really is it reasonable to treat this sample, this is a sample from an approximately normal population? And if not, explain why. Well, looking at the points here, they're kind of spread out pretty evenly as we go from left to right. All right, we're looking in this direction, or either direction really, but side to side. They're pretty evenly spaced out. Are they perfectly spaced out where each one's a certain increment apart? No, that would be perfect, all right, if that were the case, but that's not the case here. But they're not so skewed apart or unsymmetric that I have an issue with this. So this is pretty about as normal as we can get with a dot plot. So I would call this approximately normal. So it is reasonable, yes, for us to treat this as a sample from an approximately normal population. And the reason why that is because there is no large degree of skewness, and no outliers in the data. Okay, it is possible to see what we call more than one mode in a dot plot, but you got to have repeats of the values, and so you'd have to have, like, for example, like say there was a couple of extra dots here or there, so you kind of had a rise here under 355, and then again maybe you had a rise way over here. It was about the same height or equal height. Then that would be like an example of a multimodal dot plot, but you don't see that very often. Let's look at another dot plot. So at a recent health fair, several hundred people had their pulse rates measured. So a simple random sample of 6 records that were drawn. The pulse rates in beats per minute were as we see here below. And so looking at the dot plot, would it be reasonable to treat this sample as coming from an approximately normal population? The answer to that is no. It would not be appropriate to treat this like it was normal. It's not normal, and mainly because of this dude over here. That is an outlier. Look how far away from all the other data that sticks out. And so no, and simply because there is an outlier in the data, or just an outlier. Okay, simple as that. The next kind of plot we can use to assess normality is the box plot. We've seen these before. So here's an example where an insurance adjuster obtained 20 samples of estimates in hundreds of dollars for the repairs to cars that were damaged in collisions. All right. So it asks, is it reasonable to treat this sample as a sample from an approximately normal population again? So it's the same question. And when we look at the box plot, our first eyes want to go to look at this whisker being longer than the other one. All right. And it is longer than the other one, but is it drastically longer than the other one? I mean, if we look at this data value here is the minimum of that data set, and it's going to be about 4.6 to the edge of the box here, which is about 8.2, I guess. And then the whisker from the other one goes from the edge of the box at around 14 all the way up to about 16.5, it looks like. That's probably 16.5 probably. That other one might not be 8.2 exactly, it might be 8. Is there a smaller one than 8, close to 8? No, it's probably around 8.2. The scale here might not be exactly perfect, but the distance there isn't so insanely different here because the data values aren't spread that far apart. So skewness is not a concern here, even though you might want to feel that way. And so these are kind of subjective in how you look at them. But when the fact that I don't see any outliers and the fact that these whiskers aren't so far apart, and true, the median is not read at dead center, but that doesn't necessarily mean that the data set's not approximately normal. I'm looking more at the whiskers here. For example, I would say that this data set was not approximately normal if this lower whisker was any longer than it is. Like if it was about that much longer than the other one, then yeah, I'd say this data set was skewed. We have an issue, but that's pretty close. Be mindful that when you're new to this, you're not going to be a pro at this right off the bat. I don't care what you think about yourself. You're not going to be a pro at this right off the bat. It takes a little time. It takes more than one class sometimes to get really used to reading graphs the proper way, especially when it comes to assessing normality. All right, so keep that in mind. You're not going to be perfect at this at first, but through practice and seeing multiple data sets and learning how to deal with them in different ways over the course of your courses, you'll learn eventually how to do it really well. All right. But this is approximately normal. No large degree of skewness again. And no outliers. It doesn't mean that somebody couldn't come along and tell us that they think that that's skewed pretty heavily. It might mean that we probably should look at a histogram of this as well. So relying on one graph type alone sometimes is also a bad habit people have. They go, oh, I can just make a box plot and move on with my day. Sometimes you might want to make a histogram or some other kind of graph to help you determine this further. I'm going to show you one later that's the best of the bunch. Here's another box plot where a recycler is trying to determine the amount of recycled newspaper in cubic feet collected each week. And so over a course of 18 weeks, they collected the data values there below that we see in cubic feet. And look at the box plot here. This one's clear cut. Not only is it skewed, but the outlier is the first thing that it breaks right here. We have an outlier, which is probably skewing this data set, if I'm being honest. It may be skewing it more so than the data set would be if we removed it. But a caution again, when we remove outliers, I mean, it's very possible that this outlier is a legitimate data value they got. I mean, there's just more recycling that week, you know, collected just because, and that's this 4834 value here. Just because maybe that was a week where it was like a celebratory week and people had a lot more recyclables than usual. So even if we removed it and looked at the rest of the data, it doesn't guarantee that there might not be another outlier pop out. Matter of fact, whatever the value is here, the data value is here at the end of this whisker, top whisker here, might actually reflect another outlier if we removed the true outlier that we currently see and redid the box plot. We may get another outlier. So removing outliers is not always going to help you out. That's what I'm trying to get at here. But yeah, so can we treat this sample as coming from an approximately normal population? No. And the only reason you need here is because it contains an outlier. Now, what if you had a box plot that looked kind of like this? Approximately symmetric, and it had an outlier really close to the thing. That's what I'm talking about, that there's some contention out there where people believe that, well, maybe that outlier is not doing that much damage to this data set, and this is still approximately normal. That's kind of a thing you get to make a determination of when you're actually doing this yourself in the real world. You kind of get to make that decision in those cases. But for our purposes, we're going to stick to the outlier being that the data is not normal for this class. In other classes I teach, I probably would not go with that per se, but for our class, so we all stay on the same page, we're going to stick with that. I know I'm repeating myself there, and I apologize for that, but I think it's important to keep noting it. Histograms are the other kind of way, like along with the box plot. They're probably the two predominant ones you see people use, are two of the three prominent graphs we use to assess normality. And so in this histogram, they took a simple random sample of 20 pitches from a high school baseball game, and the speeds of the pitches in miles per hour were recorded. So is it reasonable to treat this as a sample from an approximately normal population? Listen, the histograms do not have to be perfectly symmetrical to be approximately normal. All right. This one is approximately normal, and mainly because there's no egregious values sticking out here. You're probably looking at this bar, and there's a gap between the 56 mile per hour versus 57 mile per hour pitches being nothing here as being an issue, and maybe that 56 is an outlier, but it's not. Because 56 miles per hour is not that great a distance from 58 miles per hour if we're thinking about it realistically. An outlier has to stand out way beyond the scope of everything else. So there's no outlier here. And if you kind of ignore that first bar a little bit and kind of look at it, the shape of the distribution kind of looks like this. And so that's not perfectly bell-shaped, but it's not so far removed from it that we couldn't be comfortable saying this data set was approximately normal. So yes, this is approximately normal because, again, there's no large degree of skewness and no outlier present. Now, in this data set specifically, what would we consider to be an outlier here? I'd be willing to bet that there's some high school pitcher out there who might be ready to go to the pros right out of high school, because it's happened. Now, that being the case, there's a good possibility that one of these values here, if that kid was pitching, could have been in the 80 or 90 mile per hour range, but we see that the pitches that were collected only go up to 63. So if there was another data value in here, and there was one pitch that the kid pitched, like say 95 miles per hour, then that would be way the heck out here somewhere, right? 95, and we'd have one little bar way out here. That would be what we'd consider an outlier in a histogram. It has to stand out well beyond all the other data values. Okay, let's look at a box plot that is definitely skewed and has issues. This one is definitely skewed beyond a shadow of a doubt. So here we've got a shoe manufacturer who's testing a new type of sole on their shoe. So they took a simple random sample of 22 people who wore the shoes with the new sole for a period of 4 months. The amount of wear on the right shoe was measured for each person. The results were recorded in thousandths of an inch. Is it reasonable to treat this sample as one that came from an approximately normal population? Hell no, it's not. This thing is skewed as all get out. I mean, just look how it falls off. This one is right. Look how long this tail is. This is right skewed beyond the shadow of a doubt. So no, there is a large degree of skewness. All right. Some people use stem and leaf plots to do this, and you can do it with smaller data sets like the ones we've been looking at. So those pictures, from the picture in high school, the one that we said where the histogram was approximately normal a few slides back. If we make a split stem and leaf plot, and you could make a basic stem and leaf plot here as well, and it would not look a whole lot drastically different. Like you could have done 3, 4, 5, and 6 here, and then just listed your stems 2, 7, 1, 1, 3, 5, 5, 8, 8, 9. The 5s have 2, 2, 3, 4, 4, 4, 6, 6, and the 6 has a 3 and a 6. Now that's pretty approximately normal, wouldn't you say, if you tilt your head? So, as a matter of fact, if you tilted your head or turn this thing 90 degrees to the left, the original image, it would look like this. And we can see pretty clearly that this is fairly bell-shaped. It's a little smidge skewed, but not enough that it should cause any concern. So is it reasonable? Yes. For the same reasons we said before, there's no large degree of skewness and there are no outliers. Okay. I'll just leave that for you guys to make notes on. Okay. Let's look at another one. This one is a stem and leaf plot that represents the sample from some population. I don't know what these numbers represent here, but it's a good representation of a stem and leaf plot that has issues. And so if I turn it on its side, we can clearly see that it just kind of falls down as we go to the right, from left to right, and so this thing is right skewed. And so no. And the simple reason here is I wouldn't consider the 81 and the 96, those might be outliers if we look at the data set further, but for our purposes here, we could just simply say no, there's a large degree of skewness. Okay. Alright, so that's the stem and leaf plots. Now this last plot we're going to talk about is one of the newer one for most of you, and because some of you, if you've taken biostats with me, we've done these plots before, but they're called the normal quantile plot, or for short, I like to call them the QQ plots, which stands for quantile plots, or just sometimes people will call them Q plots. But they go by a couple different names, but they're used to assess normality. These are a little more complex than the way that dot plots and histograms are created, and different programs, different softwares will create these slightly differently than from others, because they use the points along here, each point on this graph represents the data value either on the X or Y axis. In this case it's on the X axis, but on one of your axes is the data values. So the X in this case represents the data values, and the Y represents something we call your theoretical quartiles. All right, and these can be flipped. You don't have to have, you can have this flipped around and get the same readings basically. But so these theoretical quantiles, you notice the scale goes from -2 to +2. All right, these are z-scores. So what they're doing is they're taking and getting a percentage of each one of the values. They're seeing, like, getting a theoretical percentage underneath the normal curve that each one of these values would represent, each one of these points would represent. And then they're creating a y value by finding their z-score, and that's what's giving them their height. Or if you have them flipped around, that's what gives them their width, or the length, or whatever. And so that's what we're doing. And so this line here, which we call, is most packages call a QQ line, is basically, it's kind of like a regression line, but it's treated a little differently than that. It performs regression by not using every point in the graph, but usually what it will use is like the first and third quartiles of the graph, of the data itself. Like they'll find the first and third quartiles for the data set, and then they'll use the actual normal z-scores for the first and third quartiles of a real, truly, perfectly normal data set, and they'll find a slope and an intercept to create this line here, and the points need to fit as close to that line as possible, and if they do, then you can assume your data set's approximately normal. Now, very rarely do these fit exactly on the line like we see, but if they fit pretty close, then you can be okay saying it's possibly normal. A lot of people want to infer that points that stand away from the line are outliers, specifically like this one, the further away one stands. Now that's possibly true that those could be reminiscent of an outlier in the data set. All right, but you don't assume that from a QQ plot. Never assume that from a QQ plot, because they might not be. It just may be the nature of the way the data rolls out. Okay, so don't use these to assume outliers when you do a QQ plot. It could or could not be. It's a potential one. That's what we would refer to that as, a potential outlier. But most of these points on this graph fit pretty close to that line. There's a little bit of what I call waviness going on with the line, but that's not bad. We're going to take a look at one of these in a minute that is definitely something wrong with it. Some of my colleagues like to call when you have a QQ plot where the points hook, or what Dr. Trimboli likes to call a hooker. When the line hooks or curves drastically from that QQ line, then the data set's not normal. All right, but this one's pretty approximately normal here in this instance here. Okay, let's look at how one of these is actually made if you had to make one by hand. So I have a simple random sample of size n equals 5 is drawn, and we want to determine whether the population it came from is approximately normal. So the 5 sample values I have in increasing order, and we have to have them in increasing order, are 3, 3.3, 4.8, 5.9, and 7.9, or 7.8. So in step 1, the first thing we do is we let n be the number of values. So in this case we have 5 values, so n is 5. All right. 5 n, and then we spread the n values evenly over the interval from 0 to 1. All right, what we're going to do is find proportions. So this a sub I value here is going to be the proportions that we break down, so we get some theoretical proportions to be able to find the z-scores for under the normal curve. All right, so this is done by assigning a value of 1 over 2 to the n to each to the first sample, then 3 over 2n to the second sample, and then 5 over 2n, and so forth and so on. And the last sample you have should be 2n minus 1 over 2n. All right. So basically the last odd number before you get to your 2n value. Okay. These are denoted a sub I when you do this by hand. All right. So for example, the first a sub I value is going to be, since n is 5, then 2n is equal to 10. So this will be equivalent to saying we're going to have 1 over 10 is the value, which is equals 0.1. The next one we skip, we go 2 up in the numerator, so we're going every odd number here. It'll be 3 over 10, which will equal 0.3. And the next one will be 5 over 10, which is just 0.5. 7 over 10, which is 0.7, and then finally we're going to have 9 over 10, which is 1 less than 10 in the denominator, which is going to just equal 0.9. So that gives us all of our proportions underneath a standard normal curve that we need to find. Okay. So how do we do that? Well, step 2, we've got our a sub I proportion values for area underneath a normal curve. And for example, a sub I for that first one, just in case I'm confusing anybody, say you had a normal curve where the mean was 0 and standard deviation was 1. That first a sub I is going to fall down here on our normal curve when we find a z-score. And so the area underneath that portion would be 0.1. So we need to find the z value that fits on the curve at that point. Okay, that's what we have to do. Well, we're going to let the technology do that for us. And so we're going to use what we call the inverse norm function in step 2 for each one of these proportions to find those values. So I'm going to do in the calculator, just in case you've forgotten or are unfamiliar with it, the inverse norm function is under the vars key. So if you hit second in vars, the inverse norm is option 3. You pull that up. Yours may not look like mine. Most of yours should be defaulted to doing area to the left. These proportions we have in the a sub I column are areas to the left of the z-score we want to find. All right. It's just like the picture I drew a minute ago. It's the shaded area to the left. And so we just need to put the area in. So the first one we're putting in is 0.1. And then go down and paste that sucker in there. And I probably won't go back in here to do each one of the rest of these, but boom. I get negative 1.28 if we round to 2 decimal places. So that was normal, not normal, sorry, inv norm of 0.1, 0, 1 for the standard normal curve, and that value is negative 1.28. If we do it for the remaining ones, it's going to be 0.3, 0, and 1. And if I just call that back up there, hit second and enter, it'll bring it back up, and I can just change that to 0.3. It gives me negative 0.52. It's good customary to round your z-scores to 2 decimal places, especially if you're going to do a plot by hand. And then we need to do 0.5. So second entry, change this to 0.5. This should be 0, and it is, because that's dead center of the standard normal distribution curve. If you have 50% below, that's the median of the mean in this case of the standard normal curve. Then we keep doing it down, and I will not keep punching them in the calculator from here on out. That's going to be 0.701 and inverse norm 0.901, the area, the mean, and the standard deviation. And so the inverse, this one's actually going to be positive 0.52. And you can double check me in the calculator, and this should be 1.28. The cool thing about the standard normal curve, because it's symmetric, when we use the inverse norm function to find these proportions, because we proportion them out to be the same distance, once you get to the middle, it goes from the positive values up top. It just mirrors the same values at the bottom of the list. So what do we do in step 3? We're pretty much done at step 3. We take the x sub I values, the original data values, and the z-scores we calculated. Those will be represent our y values, and we're going to plot the points x sub I, z sub I on our graph by hand. And if the points approximately follow a straight line, then the population may be treated as approximately normal. Again, this particular small data set is approximately normal. Is it perfect? No. Do the points stick exactly to the line? No. Some people like to call this, when you're in doubt. Remember those fat pencils you had in grade school? There's a thing called the fat pencil test, where if you imagine laying the fat pencil on and it covers up the majority of the points around that line, then it's considered approximately normal. All right, that's another way people sometimes refer to that. Okay. So you can do these in your calculator without doing all that work, which is great. So I'm going to clear this out, and we're going to not do the example we just did. We're going to do a different example here. to do it. But here are the steps that you go about doing it. But I'm going to run through them here as we do this next example. So, example 10, I have a placement exam is given to each entering freshman at a large university. So we got a simple random sample of 20 exam scores is drawn with the following results. We're going to construct a normal quantile plot, aka QQ plot, using technology. Is the distribution of exam scores approximately normal? Well, let's take a look at it. The one thing that the TI is not good at is giving us, it won't give us the straight line, but it gives us enough. Now other programs, those Minitab and R, when we use those later in the semester, they do draw the line for us, okay? Matter of fact, they have a function and then it draws the line for us perfectly. And they actually look like the examples I gave you here on the last part of example 9. So to do this in the calculator, let's get to it. Pause me and put the data in if you want to follow me along. I've already done that, so I should have that data set in list 2, and I do. So I'm going to use that. And so I'm going to go over to my stat plot window, or second y equals, to get my stat plot window, and I'm going to turn my plot 1 on, but I've got to pick the correct graph here. That's the key. So once your data's in the list you want, you come down here and turn this on, and then go over to the very last graph in the bunch, and that's going to be your normal quantile plot option. Pick that, and your data set's probably going to be in list 1. Mine's in list 2, so I need to make sure I pick the correct one. And then I can hit graph. That probably won't show up if I don't have my windows set correctly, and I don't. So if I do zoom 9 for zoom stat, it shows me that, but it gave me the wrong data. That's the data from the example 9, but it drew it. So apparently I put list 1 in there again. Didn't catch myself. So let me go back into my stat plot real fast. Yep, I did. So I need to make sure that says list 2 for me. And then zoom 9, and look how that hooks. Notice how it hooks as you go from left to right. It's really crooked. Straight line through it might go from here through here, but it bends way far away from the line. This is what we would call a hooker, and it's bad. So when you see that, we cannot treat this as it's normally approximately normal. No, the points veer from the line too severely, I guess is a good way to put it. There's a lot of different ways to say this correct. Severely. I can't spell either. Probably misspelled that too, but whatever. So that's basically all you're looking for. The QQ plot is the one that most statisticians really rely on. It's the one where you're going to get the most in-depth knowledge. Now the box plots are nice at looking at different groups if you're looking at multiple groups, but the QQ plot is the one you want to see how normal your full data set is. And so it's one of the ones, I think it's the best of the 3 primary ones. Remember, the 3 primary ones are this guy, the box plot, and the histogram. And so those are the 3, but I think this is the best of the bunch. All right. Last thing I want to talk about real quick here is transforming data. We're not going to do a lot of that in this class, but you may have classes you do this in future semesters, and so it's worth noting that this is something you can do. So sometimes when we have a data set that's not normal but really wish it were, we think, oh, well, I'm going to have to do different things to this data set to analyze it further. But sometimes you can do a transformation on the data values so that your data set might become more normal. And then what you would do is you'd make the graph based on that transformation of the data being transformed. So what you basically do is, like, if you have a list of your data, you can do things such as take the square root of all the values of each value in your data set, or do the reciprocal of it, 1 over each value in the data set, and then recheck your box plot or your histogram, probably your box plot or your QQ plot, to see if it's become more of a straight line, or in the case of the box plot, if you have killed off the outliers and the skewness issue. These are not the only transformations that are possible. In a regression class, you'll probably learn there's a few more because this gets done a lot in regression analysis. But if we take the example below that I have, let's just take this data set and make a box plot of it just to see how not normal it is. All right. So just for an example here, I've already got this data in my calculator as well. I'm going to double check that it's in list 3. It is. So I'm going to go to my stat plot and turn it back to box plots real fast and make sure that list 3 is in there for me right now. Now I'm probably have to do this a couple different times because we're going to do transformations on this data in a moment. Make list 3, go up here, turn the modified box and whisker plot on, and we're going to do a zoom 9 again for zoom stat. And you see we have 2 outliers and the box is pretty squished to one side, so there's definitely issues with this data set. What if we perform square root? Let's make a note here. There are 2 outliers, so not normal. What if we try doing the square root transformation on each value in the data set? With technology that makes it pretty quick, we don't have to do it all at one time. So if we go back into our list editor and go into edit and then go over to list 4 for me, I'm going to highlight the name list 4 and I'm going to say let's do the square root of every value in list 3, so I can put the name list 3 by hitting second 3 in there, and if I hit enter it'll populate that with all the square roots. While we're in here, we're going to do the reciprocal version of this in a minute as well, so let's go ahead and do that one as well. So in list 5 I want to do 1 divided by the original list of data, not the one I just transformed, but list 3 in my case. So I'm going to hit second L3 to do that, and then hit enter, and voila, I get all the reciprocals of my original data set. So now we want to look at the box plot for the square root transformation in my list 4 here. So I'm going to go back into my stat plot and fix that so that I have list 4 being the option that I want to choose from. So I'm going to hit second and the 4 key, and then I'm going to do my zoom 9 again for zoom stat. And it looks like we still have 2 outliers in there. All right. So the box looks a little bit more widespread out here. So the box is improved, but we still have the outliers. So yeah, that didn't fix the issue. There are still 2 outliers. Not normal. So let's see if the reciprocal one fixes the issue. So again, I have that data set in my list 5 in this case. So I just need to go on my stat plot and change that feature to saying list 5. So let's change it to list 5. All right. And then we're going to do zoom 9 again. And wow, that looks a lot better than the other 2. That fixed it. It looks normal now, right? Or approximately normal now. Okay. Here's a caveat with this and we'll be done for the day. When you transform your data in this way and you make it all of a sudden appears normal, everything you do after the fact, whether it's finding a confidence interval, whether it's doing a hypothesis test of some sort, has to be done on the transformed data as well if you're going to be using a normal statistical method, or a statistical method that requires a normal distribution. You have to use this. But sometimes your outputs from those tests will be in those transformed values. So when you find a confidence interval, for example, the lower and upper bound for your confidence interval values will be in those transformed values. So to get the true confidence interval, you have to untransform or take them back, reverse them, to be representative of the true data set. So that's something to keep in mind when you transform data. I'm not going to have you guys do much of that in this course, but I just wanted you to know it was something that's out there and something you will probably have to deal with at some point if you take more and more statistics courses. All right, and there's even a method called the Box-Cox transformations method for determining what the best transformation for your data would be. You might would learn that in some other upper level classes where regression is required of you. Okay. So anyway, guys, hope you enjoyed this, and we will talk to you next time.